So, hello everyone to this session on TRNGs. We just heard that TRNGs or random numbers actually are very important for our 2 days crypto in the last talk. And now for this talk, we have for this session we have 2 talks. First one, please enter the stage, is given by Jivan Dang. He's a master student of Tsinghua University, and he researches hardware implementations of entropy extractors with a focus on unconditional security, to achieve high throughput post-processing for TRNG. And, well, talk will be on entropy extractor, obviously, and stage is yours.
Okay. Hello, everyone. Good afternoon. I'm Yifan Dang. The title of my presentation is Entropy Extractor-based high throughput post-processing for TRNG. This is a joint work on behalf of my co-authors from Tsinghua University, COSIC, and Wikimicro Innovation. This is the outline, which is divided into 4 parts. First, I need to introduce the background of our research. In practical applications, many security protocol or authentication systems are proposed for growing demand for public channel secure communication. Almost all protocols need secure cryptographic algorithms, and all existing algorithms need true random numbers. So we can see TRNG is hardware trusted root and the cornerstone of cryptographic security. This is a generic architecture of TRNG, which is composed of entropy source, digitizer, post-processing, which is also called conditioner by NIST, and other test modules. The digital noise source generates raw random numbers, but with some statistical defects. Most of existing entropy source cannot generate ideal random bit without post-processing. Post-processing is a function that extracts randomness from raw random numbers and improves the entropy density. There are 3 types of post-processing. First, we have algorithmic post-processing, which is very simple and easy to implement, but have many limitations. We also have cryptographic post-processing with computational security, but it is more complex. There is another type of post-processing named entropy extractor, which falls between of the first 2 types, which is also our focus. It is more complex than algorithmic post-processing, but it is still more straightforward than cryptographic methods. The main problem of existing post-processing is throughput. What we need, random bit throughput in communication center is about 40 gigabits per second. But what do we have? The throughput results of S31 complement TRNG cores fall short of this requirement, with the highest throughput is only hundreds of megabits per second. So a natural approach is we can use multiple parallel entropy source to generate random bits, but it will cause a new problem. If these entropy sources are truly independent, the post-processing is very simple and existing methods can do it. But in reality, on a single chip, the many entropy sources will be correlated due to the shared word line or temperature variation. So we need a method to extract randomness from multiple correlated entropy sources and satisfy the throughput requirement. The 2 proposed methods named Topis matrix and Trevisan extractor can satisfy this requirement. Both of them belongs to entropy extractor. This is properties of 3 types of post-processing methods. The algorithmic post-processing have compact hardware implementation with information theoretical security, but they cannot handle general bit collisions. The cryptographic post-processing can handle general collision with computational security, but they have no information theoretical security proof. there is no evidence that the output of the cryptographic post-processing will exhibit higher entropy density, which means that we cannot directly feed the raw random numbers into cryptographic methods and hope they will do the magic work. The entropy extractor offers the best of both worlds. They can handle general bit collisions with unconditional security, which is not based on any computational assumption. They usually extracts randomness from entropy source with the help of a random seed from another independent entropy source. So let's move on the main contribution of our work. The first is the improvement of Topli's extractor. The Topli's extractor is based on matrix multiplication. You take a raw random number vector and multiply it with a binary Topli's matrix and get the output. The leftover hash lemma guarantees the output will be close to uniformity. We can use safety factor ipser to denote the statistical distance between the output and the uniformity, which equals to the power of m minus k divided by 2. M is the output length, k is the mean entropy of input. So we can see k minus m is the entropy loss of the extractor. As for the development of Topli's matrix, you can see that the previous works has pushed the throughput from 100 megabits per second to nearly 7 gigabits per second, but it is still far away from our demand. And also, due to the relatively higher power consumption of GPU, we need an efficient solution on FPGA. We can use block division combined with FFT acceleration to improve the throughput. We divide the large Topli's matrix into smaller submatrix by rows and columns, and chunk the input vector on the same proportion. We just need to multiply m by k submatrix and k by 1 subvector at each time. Then we can use FFT to accelerate, and we join and accumulate all the intermediate results to get the final output. And for the actual FFT acceleration, we take a 3 by 4 Topli's matrix as an example. First, we need to expand the Topli's matrix into a 6 by 6 cyclic matrix and pad zeros for input vector. And then we use FFT to accelerate the multiplication between these cyclic matrix and the expand vector. Finally, we take the first 3 bits from the input to get the result. To reduce the signal length, we can use a modified Topli's matrix without weakening the security. M by n modified Topli's matrix is composed of m by m unit matrix and m by n minus m Topli's matrix. That means we just need to multiply this smaller Topli's matrix by the last n minus m bits from the input to get the intermediate result. And then we perform modular 2 addition with the first m bits from the input to get the final result. We designed the simulation architecture for Topli's matrix. The raw random number simulator simulates the entropy source. We convert the output of present by data transformation to non-perfect raw random numbers. And the random seed simulator stores the random seed and output m by k submatrix at each cycle. We need to point out that the raw random number simulator and the random seed simulator are only unitized only for simulation. In practical applications, they are all both from the entropy source. The matrix multiplication module receives a k-bit vector and m by k submatrix. It splits the m by k submatrix into several smaller t by k submatrix and use FFT to accelerate the multiplication and get the intermediate result. The last module accumulates all the intermediate results and the first m bits from the input to get the final output. Another contribution of our work is the first ever hardware implementation of Trevisan extractor. Trevisan extractor is composed of several single-bit extractors and a weak design. The weak design splits the total random seed into several random seed sites with a little overlap. The total seed length is D. We use SI to denote the every seed site, and the number of seed sites is M, and the length of seed site is T. We use R to denote the overlap between every two random seed sites. Every single bit extractor takes a random seed site and produce a single output. We join all the output bits to compose the total output. If the overlap between the random seed sites is not very large and the entropy of input is sufficient, then drawing all the output bits will not cause a large collision. These are two main types of single bit extractors used in Trevisan extractor. The first is XOR code, and the second is polynomial hash. The XOR code is very simple. It takes L bits from input according to the random seed and perform bitwise XOR to get the single output bit. But the polynomial hash will be more complex. It has two steps of entropy extraction. We need to divide the input sequence into S blocks in advance. The first process performs the polynomial multiplication and addition on input sequence in Gaudius field. The lambda is the seed of the first extraction. The second extraction performs the inner product between the P1x and the second seed mu. We can see that the XOR code has the compact hardware implementation, but it needs a long seed length and has a larger entropy source. But the polynomial hash is opposite. It is efficient on seed length and entropy loss, but it is more complex. So we need a single bit extractor strike the balance between them. So our single bit extractor also have two steps. The first seed is S1 and the second seed is S2. The S1 is used to select one random bit from input, and the first process takes L bits. After the selected random bit, this L bits is called XCell. The second process is a single bit strong blender. A general strong blender is shown like this: X and Y are two segments of raw random numbers from two independent entropy sources, and A is a series of shift matrices. The A1 denotes a shift of 1 bit, and AM denotes M bits. As for the single bit extractor, we just need the first term. So that means we just need to perform the inner product between the XL shifted by 1 bit and the second seed S2 to get the single output. To compare the performances of 3 single bit extractors, we use a unified weak design. The weak design simply splits the total random seed and overlaps the initial part of latter section with the final part of the former section. So we also use the theta to denote the overlap length to seed size length. This is the simulation architecture of Trevisan extractor. The raw random number simulator and random seed simulator is similar to that of Tobli's extractor. The input is fed to M single bit extractor, and the total seed length is split into M sites, with each site inserted into every single bit extractor. So in our configuration, we can see that the seed length of our work is 237 bits, which is comparable to the polynomial hash's 202 bits, and it is far better than the 783 bits required by XOR code. The last contribution is that we offer a selection guide for TNG designers to select the most suitable post-processing methods. We give an overview of common post-processing methods. The red dots denotes the algorithmic post-processing with information theoretical security. We also have cryptographic post-processing with computational security, such as hash function or block zippers. The entropy source that in this work offers unconditional security. The algorithmic post-processing has a minimum area and power consumption. When the entropy source only exhibit barriers or Markov collisions, we can use algorithm post-processing to handle it. We need to point out the Bloom algorithm is the only one capable of handling the Markov collision. In some applications, we need a constant output rate. Then the VN and Bloom is not ideal due to their variable output rate. In more cases, there will be both barriers and general collision existing in the entropy source. If we have cryptographic primitives in our application systems, then a lightweight cryptographic post-processing will be a suitable choice. But the drawback is that the lack of the formal information theoretical security proof of the entropy extraction. In the data-intensive servers, all we need to handle the entropy source, the multiple correlated entropy source. The entropy extractor proposed in this study will be a better solution. So next, we give the result and the evaluation of our work. This is the performance. This is the performance evaluation of the top-disk extractor, which gives a throughput of 42 gigabits per second. It is a huge improvement over the previous work. Compared to other cryptographic methods, it delivers 84% increase in throughput to area ratio. Well, the power consumption of our design is large due to the larger output length, but it is not a major concern in high-performance data servers where the speed is over the area and the power consumption. The Terrazon extractor gives a throughput of 1.82 gigabits per second. Among the three single Terrazon extractors, our design delivers a 73% increase in throughput to area ratio over the XOR code and 70% decrease in thin length. And also our design has the least power consumption among three single bit extractors. While the overall performance of our design may not match that of cryptographic methods, the core advantage of Terrazon extractor is its unconditional security. So finally, we give a conclusion. In this work, we implement two high-performance entropy extractors with a broader application range. The top-disk matrix has a high throughput of 42 gigabits per second, which is ideal for data centers where the speed is the most important factor. The Terrazon extractor gives multiple throughput of 1.82 gigabits per second. It provides efficient post-processing for lightweight cryptographic applications. Also, it is the first ever hardware implementation of Terrazon extractor. Finally, we give a selection guide for helping TNG designers to choose the most suitable post-processing methods according to their specific needs. The artifact of our design is also available. That's all. Thanks for your attention.
So thank you, and we can open the floor for questions. There's one. Either you use mic here, or there's one also around.
Hello. I think it's very good work. So my question is, can you share some information about the stability of the extractor and the of your work? I mean the stability over temperature.
we does not consider the temperature variation of the entropy extractor because the entropy extractor is a determining function that extracts the randomness from entropy source. So the consideration of post processing doesn't need to consider the temperature or temperature variation. Yeah.
So thank you for your presentation. I'm very happy to see that someone is finally using entropy extractors for post-processing. So my question is about conditions of the input entropy. So how much entropy do you need at the input in order to achieve these results and in order for extractor to work?
So you mean the comments used in input vector?
No. How much entropy does your entropy source need to produce in order for?
Oh, no. For the top-list extractor, we can change the rows and the columns of top-list matrix to handle any entropy density input to get the near uniform output. And for Turing extractor, we can also change different single-bit extractors to handle arbitrary input density to get the uniform output. And the Turing extractor is not a fixed extractor. You can use different single-bit extractors and different wig designs to according to your specific demands. As for my configuration, the input density demand for our top-list matrix and top-list extractor and top-list extractor is about 0.8.
All right, thanks. And just a quick question. Other than toplets and Trevisan extractors, did you consider any other?
Yes, there are any other entropy extractors apart from these two extractors, but they have the common features, and they have been common used in QRNG post-processing. So we just implement these two entropy extractors, but all of entropy extractors have their advantages about unconditional security.
Thank you very much.
Thanks for your talk. And it seems you implement a top-list entropy extractor on IPGA platform. So as you mentioned, the area is quite large. So do you think it's a weakness of your implement?
Thanks for your question. Our design delivers not only the higher throughput to area ratio, but more importantly, the unconditional security, which is the core principle of the entropy extractor. And the speed of our design surpasses that of the previous work. And this speed cannot be attained merely through hardware parallelization while maintaining the security guarantees. And the primary application of our design is high throughput TNG, QRNG, and high performance data servers, where the speed is the first consideration and the area is the second consideration. I hope I have answered your question.
Yes, thank you.
Maybe one last question from my side. So you have here optimized for directly this area throughput at the same time, right?
Yeah.
So I would expect that if you do different optimization goals, that you get kind of a breakdown for each of these algorithms. Do you have an idea if there are any point where maybe tuplets hash is more useful?
The main application scenarios of top-list extractor is data service where the speed is the most important factor. But if we want to explore the new extractors and other operations, maybe other entropy extractors can reach it, but we have not implemented it.
Okay, is there any further question? Then let's thank the speaker again. And we directly continue with our second talk, which will be given by Ying Ma. He is also a master student at Tsinghua University, focusing on TRNG research, with particular emphasis on entropy source design. So, as soon as we have the slides, we can directly start. Good. The stage is yours.
Yeah. Good afternoon, everyone. I'm Ziheng, a master student of Tsinghua University, and I'm here to present our work on the characterization of phase nodes for the robust and resilient PLL TRNG design on behalf of my co-authors from Tsinghua University and Wuxi Micro Innovation. And just now, my colleague presented his excellent work on TRNG post-processing, and now I'm going to talk about another very powerful and important part of TRNG is the digital noise source. And this research introduced a more rigorous and physics-based approach to designing and evaluating it. So before we dive into the details, let's do a quick recap of why we care so much about true random number generators for TRNGs. They are the fundamental root of trust in our digital world. They provide the unpredictable keys that in turn run algorithms like AES or RSA for some security hardware, and which then which to give the security for the private communications or IoT devices. So if we don't have such a high quality, truly random numbers at the very base, the entire cryptographic system is at risk. So to build a TRNG, we need a physical source of randomness, which is called the entropy source. You can see the entropy source all the time, like the thermal noise, the metastability, the chaotic system, or even the quantum effect. And our work mainly focus on another very powerful entropy source. It's the clock jitter. It's the timing variance of the clock edges. And this slide shows the whole architecture of a TRNG. Our work mainly focuses on two critical components. It's the digital noise source and its stochastic model. As you can see, the digital noise source contains two critical components. They are the physical entropy source and digitization model. And then we verify it by math through the stochastic model. So what's the stochastic model? It's a way to describe the complex physics of the digital noise source. And we can use it to estimate the lower bound of the entropy. Then the output of the digital noise source is the raw random numbers. And it is passed to the post-processing model to get the internal random numbers. And the whole system is verified by the total failure test and online test to ensure that the output of TRNG is solid. So next, let's quickly walk through the main subject of today's presentation, the PLL TRNG. Among various designs, the phase lock loop TRNG, which is the PLL TRNG, is a very excellent component. First, it delivers high-quality entropy. A PLL is excellent delivering the randomness into the digital bit, which means the raw output of the digital noise source can be used directly without any extra post-processing. And besides, once the PLL is locked, the jitter of PLL is known as a stationary process, which is an advantage for the reliability. And second, the PLL TRNG is a robust design, especially on FPGA platform. The PLLs are physical isolated components on FPGAs, and it has its main separate power supply, which can prevent the maybe crosstalk or interference from the surrounding environment or digital logic source. And third, it's a trusted and resilient component. The PLL TRNG is verified by models and on-chip tests, and due to the negative mechanism of the feedback, the PLL TRNG is resilient to the environmental changes, like the power fluctuations, like the environmental changes. So in short, the combination of high entropy, physical isolation, and environmental resilience makes the PLL TRNG an excellent choice. Okay, now let's quickly walk through how a PLL TRNG transfers the randomness into a digital bit. It starts with the entropy source. It's the clock jitter from two independent PLLs, the PLL0 and PLL1. In the real world, the clock's edges don't happen at perfectly interval at its perfect intervals. So we call this derivation jitter. It's the time domain of the clock instability. So you can also see it in the frequency domain, which is known as the phase noise. You can think of the jitter and phase noise as the two sides of the same tone. Jitter tells you how much timing is off, while the phase noise tells you the detailed character of the clock instability. So the second step is to extracting the entropy using a technique called coherent sampling. We use the clock from PLL1 as the sampling clock. It tells how to capture the state or phase of the cell K0. If we set the periods of cell K0 and cell K1 as the rational ratio, it means the phase of the PLLs, it means the phase of the PLL1 to capture the state is the excite and it's exact, yeah. So if the state is just before the edges of cell K1, the flip-flop may sell 0, but if it's just after, it may sell 1. So this is where we get our randomness. So the third step is to XOR all the samples. We use a simple logic which just XORs all the samples over a period of the PLL TRNG's output to generate a single rodent number. So this process is so efficient that the raw output of PLL TRNG has near maximum entropy, which means we usually don't need extra post-processing. So this brings me to the motivation of our work and our proposed stochastic model. The previous model, where a significant step forward, may oversimplify the complex physics of the PLLs. This may lead to two critical issues. First, the designers cannot quantify the subtle correlation of all the samples. This forces the designers into a costly and complex, trials and error. So the result of the design or the security is only known after it has been built. And second, perhaps more importantly, it may cause to overestimation of the entropy. It means the design is more secure than it actually is. So this means our model should be based on and justified a more deeper understanding of the noise source. So this brings me to our proposed stochastic model. We present a methodology for designing and evaluating the PLL TRNGs grounded in the physical characterization of the phase noise. We have three main contributions. First, we propose an enhanced stochastic model for the PLL TRNG, while accounting for all the correlations for the different PLL outputs. And second, we link a fundamental design parameter of PLL TRNG, its bandwidth, to the correlation of the sample bits. And third, we verify the model by on-chip jitter measurement circuits, and this method can achieve a 1.8-fold improvement in the jitter resolution. So the core of our model is to model the core of my model is the phase noise of PLL. We start by approximating the power spectral density of the PLL's phase noise. We use a simple but efficient shape called lorenzen. The key insight comes when we transfer this from the frequency domain into the time domain, where we can get the autocorrelation function. We realize that it's identical to that of a classic stochastic process, which is known as the Austrian-Uhlenbeck process. It's a stationary mean reverting process, and you can think of the process as random walk on a leash. The values is maybe wanders randomly, but it's always pushed back to its average value. So building on this Austrian-Uhlenbeck foundation, you can now propose our enhanced stochastic model. Instead of looking at the samples one by one, you can consider all the samples over a period together. The collection of these samples, since we know the autocorrelation function, it can be defined as a multivariate normal distribution. And here's the key. The correlation between any two samples is no longer a mystery. You can now give a process function of the time lag between them and PL's bandwidth to estimate it. And based on it, you can give an estimation of the entropy for the PL's output. So another real power of this model is to give a predictive tool for the designers. We can now calculate the phase correlation, and we know it is the upper bound of the actual bit correlation. So we can derive a straightforward formula for the designs. A designer can now specify a security requirement. For instance, the correlation must be below 0.1%, and he can use the function to calculate the minimum time lag between them, so to ensure that the output is rather independent. This process can be entirely accomplished in the software before any hardware is synchronized. So it can transfer the PLL-TRNG design into a predictable engineering discipline. To prove the model isn't just a theory, we built a full PLL-TRNG on the RT7 FPGA platform. The diagram highlights the entropy source of our design is the two PLLs. It's the PL1 of the two outputs. We use our model to get the design. First, we set a correlation threshold and get the all the constraints for the physical implementations and use a strip to find all the core parameters to satisfy this goal. So the platform parameters of the design, especially jitter, must be rigorously evaluated. Otherwise, a well-defined stochastic model may be an overestimation of the entropy. So to do that, we implement a differential on-chip jitter measurement circuit. And this technique can cancel the common mode noise, like the power supply fluctuations or environmental changes, to ensure that we can measure the true entropy of the randomness. It's the local clock jitter of the PL1 and PL0. So with a validated model in hand, we can now do a fully security evaluation. Yeah. Our design passed all the statistical tests of NIST and AIS-31. And here comes the most importantly part. Our design can get an estimation of mean entropy for the 0.9324, which is aligned with the statistical tests, while the practice model gave a higher value of 0.9544. And this value is slightly larger than that of the results for the NIST tests, which means it's in not compliance with the NIST requirements. So another contribution of our work is to give a much better evaluation method, which achieve 1.84 improvement in the jitter resolution. So how can we achieve that? It comes to what we measure. Previous work may focus on the period jitter, which is the tiny period variation of the clock tick to the next tick, while our work focuses on the long-term jitter. You can think of this like the total accumulated time error of a clock, and for a PLL, this timing error won't go forever. It will up to a value and saturates, and this saturated value is known as the long-term jitter. Because this long-term jitter is typically much larger than the period jitter, we can now characterize even the smallest source of randomness and ensure that our design is more precise and trustworthy guarantee. So to wrap up, our work has replaced the simplified physics of the PLLs and provide an enhanced stochastic model for the PL-TRNG. First, we provide a model that uses Austrian-Uhlenbeck process to model the PLL's phase noise and accounting for all the correlations of the sample base. And we establish a link from the design parameter to the autocorrelation it produces. And finally, we use a jitter measurement method to verify that our model is correct and it achieves a jitter resolution improvement. So I think our design provides a more secure, reliable random outputs for the especially FPGA platforms. And finally, we believe in open source. So we give all the artifacts of the research public available, and you can find it in the IECR artifacts repository for the TCAS 2025. And that's all. Thank you for your attention.
Thank you. And we open the floor for questions.
Thanks for your presentation. It seems that you proposed a new model for PL-TRNG So what type of noise source do you include? Do you consider the flick noise? In the presence of flick noise, the power spectrum follow the shape.
Yeah, thank you for your question. In our work, we mainly focus on the thermal noise of the PLL. And we don't care so much about the flick noise. It has two reasons. The main contribution of flick noise is the VCO in the PL components. And as the transfer function from the VCO to the output act as a high-pass filter, since the noise power spectra is shaped by the transfer function, it means the flick noise of the VCO is suppressed. So we can not think much about the flick noise for the VCO. But for the reference of the PLL, it acts as a low-pass filter, which means the influence, which means the input flick noise may be amplified by the PL's output. But for typically FPGA platforms, the input is come from the CHES oscillator. It's a high-quality oscillator, so it's naturally suppress the flick noise. So in our work, we mainly don't care so much about the flick noise, and we mainly consider the thermal noise. I hope this answers your question.
Thanks for your answer.
I have also an additional question. So you have assumed for your modeling of the jitter, you use the accumulated variance.
Yeah.
Now the accumulated variance, I expect, is subject to the correlations, so it's somehow affected. There are correlations between the different periods. So to which extent do you think does this impact the quality of your estimate?
Could you please repeat your last sentence?
So to which extent do you think that the correlations you expect between periods of your oscillator impact the estimate of the variance you use for your model?
In fact, the time for the correlation accumulated is changed by the design parameters, like the PL's bandwidth, like the frequency of the PL, like the, maybe I think the vector of the PL's sum divisor factor. So it's not typically an exact value of how many time accumulated we can not care about the correlation. It's specific to the design parameters. Yeah.
Are there any further questions? Then let's thank the speaker again.